Good morning, friends. Today I should be discussing the topic on fracture mechanics, and the fracture mechanics is an important topic which has been incorporated in the syllabus of second year mechanical engineering. So a very basic of fracture mechanics has been incorporated in the syllabus. So we should be discussing the part 1 of fracture mechanics. Now let us see what does it signifies. Now if you see this is a very basic introduction of fracture mechanics. Now when you go for fracture mechanics, you see there are if you go for the strength of material approach, you see there is the design. If based on the strength of material approach, there is applied stress and then yield strength or tensile strength of the material. So this means that a material is assumed to be adequate if its strength is greater than the expected applied stress. So that is the normal assumption of the designer before the advent of the fracture mechanics way of thinking machine design. So then they think that if any material can resist applied stress beyond or less than the yield strength, then the material is safe. So that is the normal approach of strength of material. We put a factor of safety, and depending on the factor of safety, we take as the yield strength for the ductile material and ultimate strength for the brittle material. If the applied stress is less than the yield or the tensile strength of the material, yield or the yield strength as I have discussed for ductile material, and if you go for a brittle material, there should be ultimate tensile strength, UTS. So if it is less than this, then it is considered that the material is safe. So that is according to the strength of material approach. Now what is fracture mechanics approach? Fracture mechanics, it replaces this term. This term is replaced from fracture mechanics, and two terms are added in fracture mechanics. So one is the flaw size and another one is the fracture toughness. So now applied stress depends on two factors. One is the flaw size and another one is the fracture toughness. So if you see that the fracture mechanics approach has three important variables rather than the two. As I've told you, the fracture mechanics approach has three important variables instead of the two. So additional is what? Additional flaw size and the fracture toughness. Additional flaw size and fracture toughness replace the strength as the relevant material property. So it represents the strength. It replaces the strength. In place of the strength, these two terms have come. Now fracture mechanics quantifies the critical combination of these three variables. So fracture mechanics deals with quantitatively taking these three variables. So instead of taking for the primitive study of the strength of material, it depends only on the yield strength. Fracture mechanics depends on both the flaw size and the fracture toughness. So these are the three parameters based on which flaw size means basically the crack size, or if there is any void. So these things are considered in fracture mechanics. So fracture mechanics basically deals with the three things. One is the flaw size and another fracture toughness. Now to study the fracture toughness, there are two things incorporated how to study the fracture mechanics. Now as we have discussed, there are two approaches of fracture mechanics. The first one is the energy criterion and another one is the stress intensity approach. So these are fracture mechanics deals with two approach. One is the energy criterion and second one is the stress intensity approach. So the first one is called the energy criterion. So in energy criterion, it states that crack extension, that is fracture, occurs when the energy available for crack growth is sufficient to overcome the resistance of the material. So what does it basically means? So it basically means that suppose this is a specimen. So this specimen is called in fracture mechanics as a CT specimen. CT, what is the full form of CT? Compact tension specimen. So this is a CT specimen. In CT specimen, there is a notch and there is a predetermined crack is there. So and this is the sigma and this is the crack length A is considered. Now it states that crack extension, that is the extension of crack, that is the crack will grow from A to A dash. This crack extension occurs, that is fracture occurs, when the energy available for crack growth, there is some energy you have to pump on the system. So that is you provided through the help of the remote stress sigma. So it states that the crack extension, that is fracture, occurs when the energy available for crack growth is sufficient to overcome the resistance of the material. So that the energy is sufficient to overcome the resistance of the material. The material gives some resistance, the material will oppose the growth of the crack. So if that energy given to the system, it overcomes the resistance offered by the material, then only crack growth takes place. Now next point comes material resistance. So if overcomes the resistance of the material, so what is material resistance? Basically it includes the surface energy, the energy present on the surface. Now second one is the plastic work. So whenever a material expands, so what happens plastically, if there is a ductile failure, so what happens? Plasticity will develop. So as you know, the plasticity is basically a irreversible process. That means it will absorb the energy. So it will not absorb the energy. So it will have to give more force to overcome the crack to go more. So that is a different topic. So I should not go in the depth of fracture mechanics. But so that is one other point. That is called plastic work. Another one is another type of energy dissipation associated with the propagation. Other types of energy dissipation associated with the propagation of cracks. So there are other types of energy association is also available. The cohesive material properties there. So these are the properties or the material resistance which is offered against the stress which is given on the material. Now mathematically, Griffith was the first to propose the energy criterion for fracture. So Griffith is the first to propose this energy based criterion for fracture, but afterwards it was modified by Irwin, IRW and Irwin, scientist Irwin, which is now is primarily responsible for development of the present version of the approach. So presently whatever has been done, that has been modified by Irwin of the Griffith's approach. Now the energy release, now this is the formulation for the energy criteria G, where G is the energy supplied to the material, pi sigma is the applied stress, and A is the crack length, and E is the Young's modulus. Pi sigma is the applied stress, which is shown over here. A is the crack length, and E is the Young's modulus. The energy release rate G, the energy release rate, if you see that the energy release rate G, which is defined as the rate in change in potential energy with crack area for a linear elastic material. At the moment of fracture, G is GC, the critical energy release rate which is measured. Now how to define it? The energy release rate G, which is defined as the rate of change in potential energy with crack area for a linear elastic material. Now what is linear elastic material? Linear elastic material means if you see that if the material is like this, that is called the linear elastic material. So what does the demand of elasticity? I have told before, whatever energy is pumped into the system, if you take out the force, that same energy will be liberated out. That means if you see the load versus deformation diagram, if you plot the load versus deformation diagram, if you give the load, this will take place. When you release the load, it will come back on the same line. So this is the demand for elasticity, and that is why it is called linear elastic material. That is when the material is linear. So normally fracture mechanics falls under two domains. One is LEFM, linear elastic fracture mechanics, and another one is EPFM, that is elastoplastic fracture mechanics. LEFM, linear elastic fracture mechanics, and another one is EPFM, elastoplastic fracture mechanics. These are the two domains of fracture mechanics. One is LEFM, linear elastic fracture mechanics, and another one is EPFM, elastoplastic fracture mechanics. Now this energy criterion is basically falls under the domain of linear elastic fracture mechanics. That means we does not we consider only if the material is only linear elastic. So according to this criteria, the energy release rate G, which is defined as a rate of change in energy with this is measured as this the value of this G is the rate of change in potential energy with crack area. So the rate of change in potential energy. So what is G? Basically, this G. The G is basically rate of change of potential energy with crack area. So as the crack area increases, so the rate of change of potential energy changes. So this is called G. And at the moment of fracture, G becomes equals to GC. Now we see that this is a specimen of infinite plate of thickness B and applied to a remote stress sigma A. So as I've discussed previously, for a crack of length 2A, this length of this crack is of length 2A. For a crack of length 2A, for a crack of length 2A, for a crack of length 2A in an infinite plate, that is, the plate is infinite. If you could see, the plate is infinite. The plate is infinite. So as is marked by these dimensions, infinite plate. So for a crack of length 2A in an infinite plate subject to a remote stress. It is subject, as it is infinite, so it's subjected to a remote stress sigma. The energy release rate is given by G is equals to, as I've discussed previously also, pi sigma square A by E is given by G is equals to pi sigma square A by E. Now at fracture, when fracture occurs, G becomes GC at fracture. When fracture occurs, G becomes GC, and the stress sigma becomes sigma F. So at fracture, G is equal to GC pi sigma square F by AC becomes the critical length and E becomes the Young's modulus. Over here you see in the first equation, sigma is called the remote stress, A is the crack length of twice crack length, and E is the Young's modulus of the material. Now when fracture occurs, G becomes GC and the stress the stress becomes sigma F, and A becomes critical length. The crack A becomes the critical crack. The crack length, when it reaches the critical, when it increases from here, when the crack length increases from here, it increases more and more over here, then suppose this crack becomes more and more over here, this crack increases more and more over here, so it becomes a twice AC, then fracture occurs. So as it has been clearly shown in the equation, at fracture G is equals to pi sigma F square into AC by E. So what happens as AC increases? Why AC increases? When sigma F becomes, if you go on increasing the value of the remote stress sigma F, when sigma, that is, there are three important points. When the crack length, as you go on increasing the remote stress, at the instant when crack becomes the critical crack, when the crack becomes the critical crack, at that condition, when the remote stress is called sigma F, and the internal resistance property that is given by the G becomes the GC, and fracture occurs. So for a constant GC value, for a constant GC value, when the value of GC remains constant, so what happens? Sigma F becomes proportional to 1 by root A. That is, the fracture stress becomes equals to proportional to 1 by root A of crack. When this becomes, if this becomes a constant, this becomes a constant property. If this one becomes a constant property, what happens? Sigma F becomes proportional to 1 by root A. Now the energy release rate G, this energy release rate G is the driving force for fracture. So now as we increase the value of G, so what happens? It is the main driving force for fracture to occur. So as we increase the value of G more and more, so how G will increase more and more? When the remote stress sigma will increase, and when the value of A will increase. So because here only when the remote stress sigma will increase, what happens? The crack length will increase and the value of G will increase. So it could be said in terms of the energy approach, the energy release rate G is the driving force for fracture, while Gc is the material resistance to fracture. Now Gc becomes what? Gc is the property, because when the value of G becomes equal to Gc, what happens? Fracture will take place. So G is that condition. G is the property of the material. G is the property of the material. It is fixed for a material. When the value of G becomes equals to Gc, then fracture occurs. So that is the property of the material. If you see for our tensile stress test also, if you see yield strength is the property of the material, because you are go on loading, what happens? The stress will increase. When the stress will become equal to the yield stress, what happens? Yielding will take place. That yield stress is a property of a specific material. It is fixed for a ductile material, it is fixed for a yield steel, it is fixed for a cast iron, it is fixed for gold, it is fixed for steel. So there are different, this is a property of the material. Similarly, Gc is also a property of the material. Now there is an assumption. That assumption is that Gc is independent to size and geometry of the crack, as because it is a property of the material. If it is really a property of the material, it should be independent of size and geometry of the material. So Gc is also, as because Gc is also a property, is independent of size and geometry of the crack. It is independent to size and geometry of the crack. Now what happened? Fracture toughness measurement in laboratory. So I have shown in the previously, for a CT specimen, fracture toughness can also be measured with the help of TPP specimen, which is called a 3-point bending specimen. There are different fracture specimens are there. So fracture toughness measurement in a laboratory for a specific material, when it is transferred to a structure, can be transferred to a structure, because that is called the transferability. If two things remains constant. One thing is that the assumption is valid, that Gc is independent of size and geometry of the crack. So then the fracture toughness measured in laboratory can be transferred to the structure. And another one is what? The material is linear elastic. As I've discussed in the previous article, if the material is linear elastic, I've shown the material is elastic and also linear. There's not non-linearity is not there. That is elastoplastic. It is not elastoplastic material. If the material is linear, that is linear elastic, and if the assumption of G is valid, then only fracture toughness measurement in laboratory can be transferred to the structure, and it is called the transferability of laboratory specimen from the specimen level to the component level. So that is one of the approach, energy based approach of fracture toughness that we have been discussed, that we discussed up to this in the part 1 of lecture. Now we should be discussing on the stress based criteria. So this is my first lecture on fracture mechanics, the part 1 lecture, which is based on energy criteria, Griffiths criteria and Irwin criteria. So the next upcoming lectures should be on the stress based criteria. So if you like my lectures, so please put a like mark on it, and if you think, you could subscribe to my channel for more videos. Thank you. Have a good day.